difference between previous problem and this one is, earlier two problems you have solved and it was point load. See, here you have a uniformly distributed load. That is the difference when you want to find the plastic moment or the collapse load. So what is the letter for finding collapse load? WC. C, collapse, what is W? Load. So if you want to find collapse load, you want to find WC. And what is MP? M suffix P. P stands for plastic, M stands for moment, plastic moment. See, in this problem, a 3-span continuous beam is given here. They are asking to check you that whether ISMB 225. So this is a section in a grade of 410 steel. Either this is suitable for the given load. So this is a continuous beam which is having a uniformly distributed load for 30 kilonewton per meter throughout. And it may be assumed that beam is adequately braced. All the conditions are here. Okay, what they are asking is either ISMB 225 is enough for plastic design. Now you have to check that and say, okay, you have a continuous beam and it is going to get collapse in a particular load. First finding the plastic moment, and you will be getting that MP value, and with that MP you can check with the Indian Standard Code. How to find the plastic moment? You can use plastic analysis, and first you can take the span A and B. See, in this beam, where are the points you will be having plastic moment? Do you have plastic moment at point A? So what support is this? Hinged support. Will you have plastic moment at hinged support? No, you will be not getting plastic moment at this hinged support. Okay. What about D? The same condition. This is a hinged support, you will be not having plastic moment. Okay. What about B? Will you have any negative moment here? You will be having negative moment, hence you will be having a plastic moment at point B. Will you have negative moment at point C? Yes or no? Yes, you will be having negative. So plastic moment will be there at B and C. Will you have any negative moment at joint D? No. The moment will be 0 here, hence you will be not having plastic moment at joint A and D. You will be only having at B and C. And at the span, wherever you have load, at that point you will be having plastic moment. Let us take each and individual span and we shall find. So there is a theory, if you have a uniformly distributed load, what is this ratio? 0.414 L and 0.586 L. At this point you will be having a hinge. If you are having a simply supported beam, at both the sides you will be having the plastic moment at exactly at the center. But one end is having a negative moment and one end is having 0 moment, in the sense you will be getting the plastic hinge somewhere around 0.414 and 0.568. So this is that equation. So you have a derivation for that. So we are not interested now. Exactly at this point you will be getting the plastic hinge. So you can take this diagram. And how will you find the mechanism? So this drawing is known as the mechanism. So plastic mechanism. So how will you find this mechanism? You will be using internal work done equal to external work done. This is your equation. Okay. Will you get same theta at both the joint? No. Why? Because this is not equal. If your plastic hinge is occurring exactly at the center, you will be having theta and theta here. If your plastic hinge is not occurring at the center, you will be having different theta and the another value will be not equal. Okay. If this is the case, you can take this as theta 1 and theta. How to find this distance? You can use tan theta. If you are using tan theta 1, so what will be your answer? Tan theta 1 equal to, what is this length? 0.414 L. You can take this as delta, del. You will be getting that answer, and you can equate to what is this distance? 0.586 into del. So you can equate both the answers. You will be getting theta 1. If you need theta 1, cross multiply this and you will be getting theta 1 as this value. For finding the external work done, load into distance. Whatever is the distance here, this is the formula to find. In case of UD, load into area. So your formula is not load into distance, your formula is load into area. For point load, what is the formula? Load into distance. For UDL, load into area. Okay. Now, what is your load here? 30. A uniformly distributed load of 30. What is the area? Is area of this triangle. How to find the area of the triangle? Half BH 0.5 into what is the base? Base is 5 meter and what is the height? Height is del. Either you can write del in terms of 0.414 L theta 1 or you can write 0.586 L theta. Okay. Now this is your formula. How to find external work done? Load into area. Load is WU. You can take this as a constant, write WU into what is the area of triangle? Half into total distance. Total distance is L and this height is 0.586 L theta. Now your external work done is over. How will you find internal work done? How many points you are having plastic moment? Here there is no work done. Why? Because you have a hinge. Will you have MP here? Yes, you will be having a breaking point and you will be having MP. So MP into what is this angle? If you add theta plus theta 1, add this two value. So what is theta 1? 0.586 by 0.414 theta. So MP into theta plus 0.586 by 0.414 theta plus you have a plastic moment at this hinge MP into theta. Equate that, you will be getting the value of MP. L and L will get L square and you can divide 0.586 by 2. Okay. Now find the internal work done. What is internal work done? MP into this theta plus theta 1 plus MP theta. This is your answer. If you add this, instead of theta 1, what do you have to substitute? This value. If you substitute, you will be getting internal work done. MP theta plus MP theta plus this value. What will be your answer? Which is finally, if you add all the components, 3.415 MP theta, which will be your answer. See, if you equate that, you can substitute WU. What is WU is the load. Whatever, see, earlier before the problem, we have taken it as a constant and now you can substitute that WU is 30 and L is 5 here. So you substitute both the values, you will be getting the answer as 64.34. Are you getting that? Yes. So it will be in terms of kilonewton meter. So this is your plastic moment. When the span AB is getting collapsed, it achieves the moment of what? It achieves the moment of 64.34. Then it gets break. So you are finding that the plastic moment for the span A and B. If you want to find plastic moment for the span BC, how to find external work done? Is load into, load is WU, the distance is L and this is the delta. So during the mechanism you will be getting 3 theta. Okay. Now how many plastic hinges will be there? MP theta and MP2 theta. So you will be having this values and if you add that you will be getting 4 MP theta. and this value will be the same, and if you need MP, you can cross multiply this. 4 will go this side, theta and theta will get cancelled, you will be getting WU into 2.25 MP, 67.5 kilonewton meter. Now what will be the plastic moment for the span C to D? Same as AB, hence you do not want to do that, or you can write below that the span C to D, which is similar to A and B, hence MP will be MP equals 64.34. This is your MP value, you can write that. Now what is the highest plastic moment in this 3 span? At the span BC you got 67.5, and for this plastic moment you have to check either the section is safe or not. How you can check that? You can check by using code book. Take the annexure H. Now you have at the page number 139. Take the page number 139. From 138 you have the section criteria. Now you can find ZP. First you have to find ZP. What is the formula for ZP? Equal to MP divided by Fy. So what is your highest MP here? 67.5 divided by what is the Fy given in the problem? Fy is 250. If you divide that, you will be getting 270 into 10 power 3. So this is the required plastic modulus. So you have to take a section from the code book that whatever section modulus greater than 270, you can take it as a section and you can proceed. So you check that the ZP in the tabular column should be above 270. It should be more than 270 into 10 power 3 mm cube. You check what section is available more than this. Check whether an ISMB in Fe410 steel would be suitable section. This is your ISMB 225. The value for ZP is 348. What is the required ZP for this problem? What is the ZP required? 270. Now ISMB 225 is more than 270, that is 348, hence your section is safe. So you can provide that I section and it will be safe to proceed. They are asking that UDL is given for a continuous beam, you are finding the plastic hinge, how it will break, and you are checking that either ISMB is sufficient or not, whatever they have given is sufficient or not. That is plastic analysis. Okay, now you take down another problem, find the plastic moment for the given continuous beam. What are the different types of support here? A hinged support, rest of the things are roller. And what is the odd one here? This lambda. This is load factor. What do you mean by that? Load factor. If they are giving any load here, you should multiply the load by the factor. So what is the load factor they have given? 1.7. So whatever the load is given, you have to multiply into 1.7. So if 10 is given here, multiply 10 into 1.7. Now your load will become 17. There are two factors which should be used in the design. What are they? Material factor, load factor. These two factors should be used. When you are solving any problem, if the load is given in the data, you should multiply by what? Factor of safety. You are multiplying in design of concrete structures, isn't it? The same way you have to multiply load factor in terms of steel structure. Multiply the load by 1.7. If this is 30, multiply it by 1.7, you will be getting this value. Now you should take this load factor value and you have to solve. Okay. Now what is the another improvement in this problem is they have given 2 MP here. What do you mean by 2 MP? In the previous problem they have not given anything in the beam. But in this problem They have given for span AB is 2 MP, for span DE is 1.5 MP, for span EG is MP. When you are writing the mechanism, now you are writing the mechanism. When you are writing the mechanism, in previous problems you had only MP. Now you have to write 2 MP. Why? They have given in data that it is 2 MP. If your span is empty, you can take it as MP. If your span is not empty, they have given any values, you have to take the same value here. Now take down this individual span and write the mechanism. After writing this mechanism, so due to the span, since this is UDL, what will be the ratio of the plastic moment? 0.414 L. So what is 414 L? 0.414 into what is your L? 6. If you multiply, what is your answer? 0.414 into 6. 2.582. They have written here. Okay. Then what is 0.586? You multiply it by 6. Are you getting this? If you have UDL and one end will be having negative moment and another end will be not having any negative moment and plastic. So you have to take this as your range. Now your first mechanism is ready to calculate load into area. Now what is your load here? 17. What is your area? Area is half BH. So half into what is your breadth? 6. And what is your height? Del. How will you find this del here? You can apply tan theta. You have to take this as theta and this will not be same. This you can take it as beta. How will you find this component? Both the tan will be equal. Both the tan value will be equal. You can apply tan theta equal to del divided by 2.582. Another tan value is tan beta equal to del divided by 3.418. So you can equate these two. Your beta will be cross multiply here. Beta is 0.755 theta. Internal work done. This is MP, which will be 2 MP. You have to take that theta, it is taken here, and what is beta, which is already found here as 0.755. Add this plus this is 1.5 MP. How this become 1.5 MP? Why? Because from the span B to E, the value is 1.5 MP. Okay. Now if you add this, you will be getting 4.64 MP theta. Now you equate 4.64 MP theta equal to, here this value will be 131.682 theta. Your MP will be, if you divide this value, 28.36 kilonewton meter. This is a intermediate span. You will be having plastic moment at the joint B as well as the joint E. Okay. So in the previous cases you had only one load in a span. It might be span A and B or previous problem. You had only one load. If you have two loads, what you have to do is, per load you have to take a mechanism. That is, if you are taking 51 kilonewton, you have to draw a mechanism, that is, at the 51 kilonewton of load, you will be having a plastic hinge. Then you have to go for the same concept. In that you will be getting 25.5. See, at the load of 25.5, you are getting the maximum failure. So you have to take two kind of mechanism. So this is your understanding. How many loads are there? That much of mechanism should be there in your problem. If you have 3 number of loads, you have to take 3 number of mechanisms. So this is the concept. Okay, when we are taking this span B and E, they have given 30 lambda, but we have taken 51. Why? So they have given a factor, that is load factor, isn't it? So they have, since they have given a load factor, we have to multiply by that, which is 1.7. Hence we got 51 and 25.5. Okay. We are taking that 51 is the highest load, that is due to this 51 kilonewton you will be getting the plastic hinge. So this is the first mechanism in the span B and E. At the joint B you will be having a hinge. Why they have given 1.5 MP is, see, at the joint B you have the 1.5 MP category, and at the joint E, so what is your category here? Only MP. So you have to take MP here. Okay. Now at the center of the span you will be having 1.5 MP. Are you getting the same answer for this angle and this angle? It will be different, yes or no? You will be getting different answers, that is different theta, hence it is taken as theta and beta here. So two different types of angles. How to find the angle theta and beta is, see, what is the common factor here? Is del 1 is the common factor. You can equate that. How to find del 1 is, you can use tan theta opposite side by adjacent. So your opposite is del 1 and adjacent is 2. This will be equal to what? Tan beta, that is opposite delta 1, adjacent is 4. So you can equate that. So tan and tan will get cancelled. You can equate 2 theta equal to 4 beta, and you can bring that 4 outside. You will be getting beta as 0.5 theta. So if you want to find internal work done is, internal work done depends on the plastic moment. So how many plastic moments are here? First one is 1.5, and what is the rotation? Theta. So 1.5 into theta plus the second component is 1.5 MP into theta plus beta. So theta you already know, beta is 0.5 of theta. Next you have another MP here, MP into what is the rotation here, which is beta. So you already know beta is 0.5. If you substitute you will be getting 4.25. Then for external work done, it depends on the applied load. Note the difference between internal and external work done. Internal work done depends on moment. External work depends on force. In all the previous problem, you find the difference. Always internal work will be depends on moment. Moment is internal, it is not visible. Load is visible, yes or no? If you are keeping a bureau or a fridge in a beam, it is visible. Can you able to view the moment? Moment is inbuilt. You know that this beam is carrying some moment. Can you see that? No, we cannot see the moment. You can only see the load, you cannot see the moment. Can you see the shear force? You have a beam, you definitely know that for a beam, you will be having bending moment and shear force. Can you see that? You cannot see bending moment, you cannot see shear force. Can you see deflection? Yes, you can see, no. If the beam is bending, you can see the deflection. If you have a proper apparatus, you can see that. Certain characteristics you can view it, certain characteristics you cannot view. So these are all internal property. What are internal property? Bending moment, shear force are internal. What are external? It is visible. Those are the loads. So you have two loads which is visible, 51 into del 1. So what is del 1? Del 1 you can find by using tan theta. So you can take this triangle. How to find this del 1? You can use tan theta equal to opposite is del 1, adjacent is 2. So del 1 by 2, you can find this theta. Since your angle is small, you can remove this theta and you can find that answer. Okay, if you want to find del 2, you want to find del 2 in the sense del 2 by 2. This is your equation. Now you can simplify this, that is, since angle is very small, you can remove theta and you can cross multiply this. So del 1 will be 2 theta, del 2 will be 2 beta. You can substitute here 51 into, so what is the distance here? 51 into del 1, 25.5 into del 2. After substituting this, instead of del 1, you can substitute 2 theta, instead of del 2, you can substitute 2 beta. Both are substituted. You already know what is beta. Beta is what? 0.5 theta, you can substitute 2 into 0.5 theta. If you add everything, you will be getting 127.5 theta. Now you can equate 4.25 mp theta equals 127.5 theta. Both the things will get cancelled, you will be getting mp. What is your answer? You will be getting 30. You equate this, divide this, you will be getting 30. Now the next mechanism is, you have to take 25.5 as the plastic moment. Now you draw your third mechanism. Same letters you can use. This we can take it as theta and this you can take it as beta. The same values, this is del 1 and del 2. Here del 2 will be higher. Okay, if you want to find theta, what you can do? Take the tan of that del 1, you can take this triangle. If you need del 1, use tan theta equals del 1 by 2. So you can remove tan, del 1 equal to 2 theta. The same way you can find del 2. You can take this small triangle and find del 2. Tan beta equal to del 2 by 2. So remove the tan, cross multiply the 2, del 2 will be 2 beta. Since you know beta value, so what is beta value is 2 theta. How you found this? This is the center point where two angles are meeting the same value. You can use 4 theta equals 2 beta. From this you have found that beta equal to 2 theta. Now all the components are known here. You can find internal work done. Here you have mp 1.5 mp into theta, mp into beta 1.5 mp theta plus beta. This will be your answer. Instead of beta you have to substitute 2 theta. If you substitute this, you will be getting the answer as 8 mp theta. External work done. 51 into del 1, 25.5 into del 2. You know del 1 and del 2. Both the values are known. External work done as 204 theta. Yes. Then you can equate 8 mp theta equal to 204 theta, which is 25.5 kilonewton meter as your mp. Now you can go for the span E and G. Since you will be having one side as mp and another side as, you will be not having mp, this is another value. Hence you will be not having the load at the center. There will be slight deviation. Slight deviations will be there. You can take theta and beta. You have to find both the components. If both the plates are having the hinge, then it will be exactly acting at the center. If both the hinge are not same, both the end condition are not same, you will be having slight deviation. Yes, your internal work done will be mp into theta, mp into theta plus theta. So you can take beta as also theta. Hence you will be getting 3 mp theta, and for external work done, load is 34 and distance is del. So your del is 2 beta, or you can take 2 theta. you will be getting 3 mp theta equal to 68, which will be 22.67. Now, what is the worst case here? At which place you got the highest plastic moment? At which span? At the span BC, you got the critical value of 30 kilonewton meter, which is your critical plastic moment.